This problem is number 24 in chapter 7. And we have an interesting setup here. We have a 1 kilogram block, we're going to call block A, sitting on top of a 2 kilogram block, we're going to call block B. The 1 kilogram block A is actually tied to the wall with a rope. The 2 kilogram block, we have a 20 Newton force on a rope that's tied to it and is pulling it away. It's going to accelerate out from under block A. So part A, we want to figure out what the tension is here in the block, in the rope that's holding the block to the wall, and what's the acceleration of block B is part 2. So we start these like we start all of them. We have to have a free body diagram. So we're going to do a free body diagram. Actually, I'm going to do it down here. Just remember what we're looking for. So for block A, our free body diagram has MA times G, M sub A times G. And then remember, we don't have a normal force. It's sitting on top of another block. So we have force of B on A. Okay? And then we have a tension force going this way, which is T1. We also have a friction force going this way. As block B slides out under block A, it's the friction force between these two is making the block move that way. Essentially, from block B's point of view, block A is moving that way, so the friction is going the opposite direction. Okay? So this is friction force, kinetic friction of B on A. Okay? We know the friction force has to balance T1 because block A isn't moving. All right, let's do the free body diagram block B. Block B, on the other hand, has more mass. It has a normal force coming from the ground. And it also has, if there's a force of block B on A, there has to be a force of block A on B. So there has to be another force going this way, force of A on B. Notice these are a third law pair, and we want to mark the third law pairs. Those two correspond to a third law pair. The force of B on A is exactly equal and opposite to the force of A on B. Also, we have this T2 tension force going this way. And we have friction. Now we have two frictions. That's why we have to label them different. We got a friction, kinetic friction from the ground. I'm going to call it G. And we have kinetic friction of A on B. Block B is feeling friction from the ground and from the upper block. So there's two frictional forces on it. So there you go. Now you have our free body diagram. I'm going to make this longer because the tension here has to be greater than those two added together because it's accelerating to the right. Okay, so block A, up here we're going to do F net X. F net X is the friction force of kinetic friction of B on A minus T1 must be equal to the net X force. But block A isn't moving, so this is 0. So we can say that, oh, well, T1 is just equal to friction force, which is mu sub K times the normal force. But there's not really a normal force. What it really is F of B on A. The force that this block is applying on there is what the frictional force is going to be. Instead of normal force, it's the normal force, but it's a contact force. Then, to figure out what that force is, we got to do F net Y. Well, F net Y is going to be F of B on A minus M A times G. That's supposed to be an A. I couldn't read my own writing. That is also 0 because the block is not going up or down. So I can say that, oh, F of B on A is just equal to MA times G. Now I'm going to plug that back in here, right there. So T1 is equal to mu sub K times MA times G. Well, I know all those values, so I can plug that in. It's 0.4 times 1 times 9.8, and I get tension in the rope connected to the wall is equal to 3.92 newtons. All right. Now, we have to do block B. Block B. Block B, we're going to do F net x. It's going to be equal to T2 minus the friction of, kinetic friction of A on B, minus the kinetic friction from the ground. I think that pen is done. But this block is accelerating, so this becomes mb times g is equal to T2 minus the kinetic friction times the force of A on B, but we already figured that the force of A on B has got to be the same as B on A because they're a third law pair. And if they're a third law pair, by the way, I missed one third law pair too. This is also a third law pair, right? So I'm going to do 3 slashes here. And that one is equal to, so the frictional force here, I mean the force of A on B is equal to B on A, which is equal to MAG. So I can put in MAG right here. This is with respect to the ground, but that's the normal force. I haven't figured out what the normal force is. So let's figure out the normal force. So we're going to do F net y. Well, F net y is just going to be the normal force minus F of A on B minus MBG. And this is going to be 0, so we're going to say the normal force is going to be F of A on B, but we already figured F of A on B is F of B on A, which is equal to MAG, so this is going to be MAG plus MBG. Or it makes sense that the normal force has to be equal to those two added together. So I'm going to plug that back in to there. So, coming back down here, I got MBG is equal to T2 minus mu sub k MAG minus mu sub k times, I'm going to replace it with all this, MAG plus MBG. Okay. Oh, sorry. This is not G. I don't want to put a G in there. That's A, right? It's accelerating. And so to get the acceleration now, I'm going to solve it for A. So A is going to be 2T2 minus mu sub k MAG minus mu sub k MAG plus MBG, all divided by MB. All right, I have all those numbers, so I can just plug all this in. Tension 2 is equal to 20 newtons. They gave us that, so we have 20 minus 0.4 times 1 times 9.8 minus 0.4 times 1 times 9.8 plus 2 times 9.8 all over 2. And when you plug all that in your calculator, you get A is equal to 2.16 meters per second squared. Or 2.2 meters per second squared because we only have 2 sig figs. And that's how you do number 24.